here. And on behalf of my colleague Preeti Khanna Madam and myself, I welcome you to this session, Dr. Mohanty. Please, can you please begin? Neha, have you started live streaming?
Yes, ma'am.
Yeah, it is started. So thank you, Sraban. Thanks a lot.
Thank you, ma'am, for your lengthy introduction. Okay, let me to share the screen.
You deserve much more than that, Sraban.
No, ma'am, it's the longest introduction I have ever heard about. So, for all participants, I thank Professor Oja for her generosity. However, I still think myself as a student of clustering. I am not a researcher. I am still a student. I am learning like you. So hopefully we will learn together. So is it visible now to all?
Yes.
Okay. So should I switch up my video or?
Yes, you may switch off because today, because of this exam, the
There will be streaming.
quality of signal is very poor. Exam going on in our campus. Yeah.
Okay. So very good afternoon. Today we'll discuss clustering algorithm, which is basically unsupervised learning. I hope you have fair bit of idea now about what is called learning and mainly the supervised learning. So today we'll discuss unsupervised learning. Mostly the clustering algorithm is a synonym for unsupervised learning. Okay. So as you might have already seen several lectures on supervised learning. This is classification is seen as supervised learning from example like human learning from past experiences. Computer systems learns from data which represents some past experiences and we gather such past experiences through data, and then we trained a model. We trained a target functions that can be used to predict the values of a discrete class attributes, like for example a bank loan is going to be approved or not approved, the patient is a high risk patient or low risk patient. So the task is commonly called supervised learning or classification. And this is one example. You might have gone through several applications of supervised learning algorithms. So suppose a credit card company receives thousands of applications per day to issue new credit cards to customers. So if each application contains several information about an applicant, maybe its age, marital status, annual income, outstanding debt, credit rating, now we have credit scores and so on. So the problem is to decide whether an applicant should be approved, or to classify applications into two categories, approved or not approved. Based on that, the bank can take a decision. So such kind of modeling are examples of supervised learning. So in the unsupervised learning, what is that then? So can we have data having no labels where previous or past experience is not available with us, and still if you want to find the inherent groups hidden in the data, can we able to identify or discover such hidden groups? So I'll give you an example. Suppose first time you have never visited a city and you do not know the geographical location of the city, let's say, and first time you are flying over a city. So from top, when you look at the city just before landing of a flight, let's say, when you look at the city, you can easily identify the forest lands, commercial places, farmlands, riverbeds, etc. Though you are first time visiting the city, you have absolutely no information about the city. So class labels are not known. Which portion of the city is hill area, which portion of the city has forest lands, which portion of the city has farmlands, probably you do not know, but still by looking from the top you can still able to identify there is a river going through the city, and this is a city area, this is probably the river beds, etc. How do you know? So this is a classical example of unsupervised learning, where though you do not know about the city, but just looking at that you still can able to identify or discover the different portions of the city, right? So this is an example of an unsupervised learning. So in the unsupervised learning, basically we call clustering. The class labels of the data are unknown to you. That means the past experience is not available. So given a set of data, the task now is to establish the existence of classes or clusters hidden in the data, or discover the clusters. So this is one example, some data points in a two-dimensional plane. So if you visualize this, probably naked eye, we can say there are three groups hidden in the data, right? So no training is required, nothing, no class label is known, just the data is given and you are supposed to identify the hidden groups. The main question is finding groups of objects such that the objects in a group are similar or related to one another and different from the objects in other group. So here there are three groups, right? So if you want to identify the objects, if you want to identify the suppose this is one group, right? So if you take any two objects, these objects can be two images, the profile of two persons, etc., or two documents, or two news articles. So if you find any two objects in a group, you find they are much more similar to each other than when you compare any two objects belonging to two different groups. So if you take these objects and these objects, probably you find the similarity between them is too high. The dissimilarity is too high. So we'll quantify what is called similarity and dissimilarity. But we say the objects are highly similar when they belongs to a single group, and they are highly dissimilar when they belongs to different groups. So how to find such hidden groups so that these two objective criteria are satisfied is called a clustering problem, where the first criteria is to minimize the intra cluster, this is intra cluster, within a cluster similarity, to maximize within cluster similarity, and also to minimize the between cluster similarity. So this one is called cohesion, when you want to maximize the intra cluster similarity. And this one is called separation. So these are the two objective criteria to satisfy when you are constructing or developing any clustering techniques. So I'll start with few applications, then I'll go to the techniques. So one of the application is market segmentation. Let's say a retail company may collect the following information on households living in a particular location. Can be the income, can be household size, how many members are there in each family, occupation of the household's head, the distance of the household from nearest urban area, right? So many data can be collected about a family, and then can identify the following clusters based on the available data. So what are those clusters? One cluster can contain all the families having a smaller family and high spenders. Cluster 2 or another group can have families having larger size and high spenders. Cluster 3 or third group can have small family and low spenders and spenders, and then cluster 4 can have large family and low spenders. Then the company can then send personalized advertisement or sales letters to each household based on how likely they are to respond to specific types of advertisements or products. So if a high values product is launched and it is useful for a larger family, so most likely they are going to send personalized advertisement to cluster 2 or the households which belongs to cluster 2 and so on, right? So this is one of the examples of application of clustering. And one more example which is very popular examples or have a lot of application nowadays is document clustering. In the document clustering, the goal is to find groups of documents that are similar to each other based on the important terms appearing in them. For example, every day millions of news articles are being published. So many of them are related to sports, and within sports there are several, suppose cricket related articles, tennis, football, and so on, right? And then there are political news articles, there are economic news articles, and so on. So based on the words in them, can we able to group those news articles, right? Which articles are related to sports, which articles are related to finance, which articles are related to politics, and so on. Can we able to do this? So this is another application of clustering. So maybe while using your mobile phones, suppose you someday you might have clicked on some news article related to sports or maybe finance, and next day you will see that 50 news articles which are related to sports and finance will be displayed in your mobile phone, right? So how do they find all such groups of news articles which are related to sports or which are related to finance, right? So that is where the clustering plays an important role. So given the important terms or words in the document, so based on that, you can classify the documents into different inherent groups like sports items, and within sports you can have different groups like cricket related articles or football related articles or tennis related articles and so on. So, right. So these are applications of clustering. Clusterings are everywhere, right? Another very important application of clustering is summarization, where you have very large data sets and you are unable to model, suppose for any application, processing huge amount of data is always a challenge. So can we able to summarize the whole document? For example, in the document clustering, the text summarization is one very important problem nowadays. A lot of people are working on natural language processing. Given a large documents, let's say thesis of a PhD student, can you able to summarize the thesis? For example, can you able to write the abstract of the thesis? So that is called text summarization. So this kind of things can represent a larger data sets by a smaller number of objects, right? So that is another application of clustering. In fact, clustering is one of the most utilized data mining techniques. It has applications everywhere. It's a long history of applications used in almost every field. For example, medicine, botany, sociology, biology, marketing, and everywhere. So we'll not go deeper into what are the applications of clustering. What we'll concentrate in today's lecture is we'll concentrate on the basics of clustering, how what is the basic principles of forming the clusters, and we'll see one or two techniques to cluster unlabeled data. So what is not clustering then? Which kind of problems are actually not clustering? So many such problems you might have already seen in the supervised classification. So if the data has class level information, you trained a model, you construct a target function by training the data and then giving a new instance, new object, and then you can classify it, where the groups are discrete groups, right? Man or woman, like, or animal or man. So those are discrete groups. So that is one example of that is an example which is actually not a clustering problem. Simple segmentation. Let's say the students' data is given to you, and there are you can group them based on their different registration groups alphabetically, right? let's say the surname starting from A, surname starting from B, surname starting from C. That way you can group the class of students into different groups, right? So that is not an example of clustering, right? Then result of a query. Suppose you have a database and you supply a query and you get some results. So that is again based on the query. Let's say whose annual income is greater than 10 lakhs. So that you will find set of objects which have having the annual income greater than 10 lakhs or less than 10 lakhs. So you can have two groups, but that is not example of clustering, because groupings are a result of an external specification, that is your query. So clustering is a group of objects based on the data, inherent group of objects based on the data, not based on the external specification. So the clustering notion is actually very highly ambiguous. That's therefore we'll see that why it is a challenging problem always. So we'll see that suppose this is a two-dimensional, some data points is given in a two-dimensional space. So how many clusters are there in this data, right? If this question is asked, how many ways you can probably, if you ask this question to different human beings, let's say this set of points are visible. Now tell me in your perception, how many clusters are there? How many two different groups are there? So probably the answer will be many. So one answer is can be there are two clusters. So here it is shown in by different colors, right? Because it look like there can be two clusters. Somebody can say no, there are 6 clusters. So they are shown in different colors and different shapes. This is one cluster. This one is in yellow in one cluster, then blue in one cluster, green in one cluster, purple in one cluster. So there can be 6 cluster, and then somebody else can say no, for there can be 2 clusters. It is the clusters are shown in different colors. So if you look at the third picture, there are 4 clusters in the data. Then the next question obviously will be whether this group really contains 2 or 4 or 6 cluster. Which one is the best answer? How do we know this, right? So therefore it's always a challenging task to know how many clusters are there. In many applications you will find number of classes are known to you in priori. So you can find that this many clusters are there. So that can be an external parameter to find out, to discover the clusters, that k number of or 5 clusters are there. You identify 5 inherent hidden groups in this data. Otherwise, in many applications, even the number of clusters, number of hidden groups are not known. So you have to identify such groups from the data, right? So once you identify such groups from the data, the next question will be which 2 groups or which set of clusters are the proper or best clusters. So these are the different aspects of clustering. What are the important factors which can influence the clustering, right? So first or most important factor is the clustering algorithms, right? There are many algorithms exist in the literature, like supervised learning. You might have heard about KNN or many other supervised learning techniques. Similarly, in clustering, we have many popular clustering algorithms. Even thousands of clustering algorithms exist. It is being developed also nowadays, right? Almost every month you will find several research papers which develop new clustering techniques, advanced clustering techniques. So there are many techniques. One such very popular technique is called K-means algorithm. Then there are hierarchical clustering algorithms. Then we have DB scan. Those are very popular and historical clustering algorithms. So they influence the clustering process. How good clusters are formed from the data, that is mostly influenced by clustering algorithms. Then the next factor which has a very important role in the clustering process is called proximity function, or we call similarity or dissimilarity function, right? So how the two objects are similar to each other, or how the two objects are dissimilar to each other. So if two human beings are, somebody asks that you compare between two human beings about their nature. So you can say they are similar in nature or they are dissimilar in nature. So if I ask you uh, uh, to distinguish between any two data objects, so numerical values are only given. So how to distinguish which two objects are very close to each other, or two objects are not close to each other? For example, if two images are given to you, how do you distinguish that these two images are very similar to each other, or two images are highly dissimilar? They are not at all similar to each other. So if a image of a man or image of a dog is given and you are asked to compare if these two images are similar, so your obvious answer will be no, they are highly dissimilar to each other. So this plays a very important role in the clustering. So somehow in the human perception, it can be easy. Again, we have to say those are similar, but if in the clustering we have to quantify this similarity and dissimilarity. So how to quantify that one object, how much one object is similar to one or dissimilar to one, right? So we'll see the basic examples of proximity measure. Then once these clusters are formed from the data, or clusters are discovered from the data, the next challenging task will be which set of clusters are the best clusters. So how to know, right? So once clusters are produced, next question will be judging the quality of the clusters. So which clusters are best, or which, I think if you are posting something, I do not know the questions. You can ask me the questions directly if you have any questions.
Just a minute. It's written 2, 6, and some people are writing and somebody's writing things. Then kindly share, resend the video link. Will you please, participants, if you don't mind, please, can you do it? I mean, we have been sharing, so please don't worry. We will be sharing with you. Right now, my request is to please concentrate on this, because the speaker will not be able to see your questions if they are flooded with sharing the link and all those things, right? So, Sraban, are you not able to see this chat appearing or what?
Chat is not appearing. I have to click and see.
Okay, okay.
Automatically, it is not being displayed.
Yeah. All right.
So anyway, I have a question.
In case there is a question, we will be. I will prompt you.
Yeah. So I have a question answer session also at the end. We can take a question at that time. So therefore, the quality of a clustering result depends on the algorithm, the distance measure, proximity measure, and the application. Right? These three factors influence the clustering technique. So this clustering quality part is the post-processing. Once the clusterings are formed or discovered, how to measure, how to quantify the which clusters are the best clusters, right? So that is clustering quality. So in today's lab session, we'll see many such techniques to measure the quality of clusters. So before going to these clustering algorithms, let us briefly go through these proximity functions. The similarity measure or dissimilarity measure. So similarity measure is a numerical measure of how alike two data objects are, right? How to quantify the measure of alikeness of two data objects. So the value, this quantity or value of similarity is higher when objects are more alike to each other, more similar to each other, and this often falls in the range between 0 to 1, right? And then this similarity is just the opposite of similarity, where the numerical measure of how different two data objects are. This dissimilarity is lower when objects are more alike to each other, and minimum dissimilarity is often represented as numerical value 0, and upper limit can vary. It may not be bounded by 1, it can be anything, goes up to infinity. So what is then proximity? Proximity refers to it is a generic term to represent the similarity and dissimilarity. When the context is not very clear, that it is similarity or dissimilarity, we use the term proximity for that. Proximity refers to both similarity or dissimilarity. So what is that then? How to compute this dissimilarity functions between two data, dissimilarity between two data objects, right? So this is how we represent a data matrix, where you can see a two-dimensional matrix. It's a n cross p matrix, right? So here n cross p, when I say, 1 minute please. So this is a n cross p matrix. So this is your data matrix where the rows represent the data object and these columns represents the attributes, or we call features, or we call dimensions, right? So here there are, this is dimension 1, dimension 2, dimension p, or feature 1, feature 2 and feature p, and this is data objects 1, data objects 2 and data objects n. So this is called data, and given this data, and suppose this is data objects 1 and data objects I. So if I want to find the how much these data objects I and j are similar or dissimilar to each other, how to quantify this measure. So this can be done using a dissimilarity matrix, right? So we are only considering dissimilarity, right? Similarity is just analogous to this. So here, when you say about dissimilarity, if you look at this dissimilarity function, so it's a symmetric matrix. It's the distance between the data objects 2 and 1, distance between data objects 3, 1, 3, 2, and 3, 3. Between 3, 3 is obviously 0. They are not dissimilar to each other. They are exactly similar to each other, right? Since they are not dissimilar, therefore this diagonal values are 0. And if you look at the upper triangular values, distance between I and j is same as the dissimilarity between object j and I, right? So that is symmetric. So this is always a symmetric matrix, or the diagonal values are 0. So now the next question will be how to compute this dij values. It is not moving. So there are several similarity functions. So based on the data, so as you might have already known, the data depends upon the data. The data can be categorized broadly into two categories: numerical data and categorical data. Numerical data, probably you might have deals about everyday's life, right? It's just the numerical values, the salary, the cost of a product, right? So these all are examples of numerical data. Then another class of data is called categorical data. In the categorical data, again, is broadly classified into two categories: nominal data and ordinal data. In the nominal data, example is where the symbolic numbers are given. They are actually not numbers, they are just symbols. For example, gender, male, female, blood groups AB and O, or O positive. The phone code or country code can be India code. The US code can be 1, our code can be 91. So 1 to 91 can be the different codes of the phone code of the countries, right? So they are just symbolic numbers. They're actually they do not actually represent, or their value of the numbers have no meaning attached to it. 91 you cannot say is actually less than 1 or greater than, or 91 has more importance than 1. Similarly, there are other kind of categories called ordinal data, where those symbolic values have some order information. So which data are called nominal data, where the relationship between this data is only the distinguishable or undistinguishability. A is equals to B or A is not equals to B. So that is the only operation allowed on nominal data, right? Male is equals to female, or female is equals to male. Country code 1 is equals to 10 or not equals to 10. That is the only operation that is allowed, and such data is called nominal data. Then what is ordinal data? Again, these are the finite set of categories. For example, the length of the t-shirt. So this is small, medium, large, XL and double XL. Again, this doesn't represent any numerical value, but they can be comparable. So you say small size of small t-shirt is less than the size of the medium t-shirt. Again, the size of the medium t-shirt is less than the size or less than large is less than double XL. Similarly, the grades we give to the students, A plus is better than A is better than B plus is better than B, and so on. So such kind of data are called ordinal data, right? So when you define any similarity measure, you first have to look at what kind of data you have in your possession, what kind of data actually you want to process. You want to find the clusters, or in the supervised learning, what kind of data you have, right? So every similarity measure cannot be applied on any kind of data arbitrarily. So you have to be very careful. So depending upon the data, the categories of data, we have different similarity measure. Today's lecture, let us concentrate only about the numerical data, because that is the most widely used data, available data, and the people processes data, right? So we'll concentrate on numerical data and we'll see few popular similarity measures. So here this proximity measures for numerical data. Let's say suppose xi and yi denotes the values of ith attributes. Let's say we have two data points or two data objects, objects can be image, can be document, and the object x can be represented as x1, x2 up to xn, suppose n dimensional data. And another objects, let's say y can be represented as y1, y2 up to yn, let's say, right? So how to find the distance between these two data, the dissimilarity between these two data, right? So this is where there is a very popular distance function called Minkowski metric. We'll see what is called a metric. So this is called Minkowski matrix, where the general formula is xi minus yi, the absolute difference between attribute wise absolute difference, to the power r is any integer value, take the sum of this, and this is then again take the power 1 upon r, right? So this is called Minkowski matrix, and depending upon the particular value of r, we have different distance measures. So we say a proximity measure at this distance, actually this is called a metric. Metric is a particular term. So we called a similarity measure, dissimilarity measure, a metric, provided it satisfies certain conditions. So first condition is the distance must be always greater than equals to 0, right? Thus dissimilarity between two objects cannot be negative, right? And the distance between two objects x and y is 0 only if x is equals to y, right? This is called non-negativity rule. Then the symmetry rule, it says distance between two objects x and y is distance between y and x, right? The dissimilarity between x and y is same as the dissimilarity between y and x. This makes sense, right? Then we call transitivity rule, or we often called the triangular inequality, which says that the direct distance between two objects x and y, the direct dissimilarity between two objects x and z, is always less than equals to if you compute such distance through another object's y. So therefore it is called transitivity rule or triangular inequality. If your proximity measure satisfies all these three criteria, such a measure is called a metric. So we'll see a few examples of metrics, then we'll go to clustering algorithms. This depending upon the value of r in the Minkowski function, we called the distance measure is renamed accordingly. So the very popular one is called Manhattan distance, or we often are popularly called L1 norm, y1, because r value is 1. So in the Minkowski formula, if you just put r value as 1, this becomes d equals to I varies from 1 to n xi minus yi. So if you compute this, this is called Manhattan distance. So this there is one example here. X value is here x value is uh, uh, 735, let's say. Y is another object, so its value is 3 to 6 is three-dimensional data. So xi minus yi, if you look at 7 minus 3, then here 3 minus 2, right, and then 5 minus 6, attribute wise absolute difference, take the sum, so this is equals to 6, right? So this as a special instance of Manhattan distance. So this is called Manhattan or L1 norm. This is very popular measure. Then next is how to move next, how to clear the drawings. Then next is the proximity measure. Second is if p value is 2, then this is highly used, most popular distance measure called Euclid distance measure. You might have seen this from your school days. So giving 2 points on a xy coordinate or a plane, find the distance between them. So this metric is same as Euclid distance between any 2 points x and y in n-dimensional plane. So the example is given here, which is suppose again x value is 735. Sorry. So it is, let's say, 735, and again same data objects 3 to 6. So it is 7 minus 3 first coordinate difference, then 3 minus 2 square, then 5 and 6 minus square, and then take the whole root over, so whole to the power half. So this is 2.426. Then another one is called Chebyshev distance or L infinitive norm. So here the R value, which this is defined at maximum over all I varies from 1 to n, xi minus 1, just the difference, the maximum over the absolute difference, coordinate wise absolute difference. So here again it is 7 upon 3, 735. Sorry, it is moving. 735 and 326. So you find compute 7 minus 3, 3 minus 2, and 5 minus 6, and take the maximum, which is obviously 7 minus 3, which is 4. And if you compare this with Manhattan distance or L1 norm, you find L1 norm is always greater than the Chebyshev or L infinity norm, because this term is always there, right, and other positive terms are added into it. Then the next is clustering. So clustering is a set of clusters. The process of clustering is a set of clusters. Here there are different ways we can cluster, different techniques exist. Very popular one and widely used one is partitional clustering. There can be hierarchical clustering. Then there can be density based clustering, graph based clustering. There are many techniques exist to cluster the data. So this is, let's say, original data points. In the partitional clustering, let us say the original data points are given, how to partition them into different clusters. Right, so here you can partition them. So the technique here is how to partition the data into different clusters. Then hierarchical clustering is another technique, very popular clustering techniques, where how to find the hierarchy exists in the data. There are many places where you find the hierarchy in the clustering, let's say animal kingdom. right? So how to identify such animal species exist in the animal kingdom, right? The set of animal images, let's say, are given, and you have to classify them, you want to cluster them. So how to find the hierarchy or families of cluster of animals? So here this kind of clustering is called hierarchical clustering. So this can be done in different clustering techniques can be employed to find both this hierarchical, density based, or many. So one such technique is called OL separated clusters, center based clusters, continuous clusters, density based clusters. We'll see few in today's lecture. So one is here, let's say OL separated clusters. So when you say based on this criteria, we can identify the clusters in the data. So what is this? When we say the clusters hidden in the data are OL separated clusters. So a cluster is a set of points such that any point in a cluster is closure means more similar, okay, to every other point in the cluster than to any point not in the cluster. So the meaning of this is if you look at these clusters look like they are highly separated to each other. So is this moving? So they are separated. So how to measure when we say this is OL separated clusters? So if you look at any point here, any in this cluster, and find the distance or similarity of this point to any other point in the cluster or any other point in this cluster or in this cluster, let's say. So the distance of this point from any point or all the points exist in this data. If you compare the distance, you will find all the points within this cluster are more closer to each other than to any other points. Let's say this point or maybe a point here. So they are far apart from each other. So when such criteria is used in the clustering, the clusters are called OL separated clusters. Then there are other clusters called center based clusters or prototype based clusters. In today's lecture, we'll see the algorithm, K-means algorithm, which is basically based on this prototype based or center based clustering. So first of all, given set of data, you can always find the center of the data. So center is simply the arithmetic mean of the data points. For example, if I say two-dimensional data 2, 3 and 4, 5, so I can find the arithmetic mean of these two data points and say that is the center of the this two data points. Or basically for a sake of simplicity, let's say this is in a one-dimensional x-axis, some data points are let's say 4 and another data points is 6. So if I say find the center of this two data 4 and 6, so it's just the arithmetic mean of this 4 plus 6 10, its mean is 5. So this is the center of the data, right? So similarly, if it's a two-dimensional or n-dimensional data, you find the coordinate-wise mean. So here in this case, it is 4 plus 2, 6, its mean is 3. Here 5, 3 is 8, its mean is 4, right, divided by 2. So the center of this two data is 3, 4. So given the set of data points, you can always compute the arithmetic mean of the data. So that is often called centroid, right? This is applicable only for numerical attributes, numerical data. So today's lecture we are only considering numerical data. This definition will vary if your data is categorical, because in the categorical data you cannot able to apply this kind of operations. You can obviously apply arithmetic operations, but those operations are not meaningful operations, right? They have no meaning. Let's say there are different colors and you are simply giving them numerical values to color blue to 1, 2, 3, 4 and then finding their mean. So that is meaningless. So a cluster here in the centroid we call centroid or centers. What is that? When the clusters are called centroid based or prototype based clusters, right? So suppose this is the cluster center and this is another cluster center. This is also a cluster center, right? So if you take any data here, right, in this cluster, you find this data is closest to the nearest cluster center or belonging to the same cluster. So you find the distance of any point to different cluster centers, right? So you'll find that this data point is closest to this cluster center. Therefore, this data points goes to the cluster having this as the cluster center. So therefore, this kind of clustering is called center based or prototype based clustering. The next is called contiguous clusters or nearest neighbor or transitive clusters. So it's a cluster is a set of points such that a point in a cluster is closer or more similar to one or more other points in the cluster. So if you look at this shapes, so you find all the data points. There are many data points exist here. So you find all these data points belongs to a single cluster. So this color represent cluster. So this forms a single clusters. All the data points within this forms a cluster. This is one cluster and this
Your
is one
voice
cluster and
is
this
breaking,
again
or
all these data points are actually
participants,
it
are you able
carefully.
to? Yeah, Sraban, your voice was breaking, or I don't know. Now it is clear. Yeah, she's saying clear. So probably my side, I'm okay. Thank you.
Oh, okay.
Thank you. Thank you.
So
Sorry for interruption.
no issue, ma'am. So if you look at this carefully, you will find that suppose there is a data point here and there is another data point here. Okay? So if you look at this distance or similarity, these two data points are supposed to be very means their distance is more than a point exists here. So if you look at the distance carefully, you will find that this the distance between these two data is closer, and then the distance between these two data points is more closer. However, this data point and this data points belonging to a single cluster, and this data point is going to another cluster. Why? Because if you look at the neighborhood of this data points, so the neighborhood of this data point can be this. Let me to change the color. So if you look at a data point here, its neighborhood can be here, its neighborhood can be here, this point can be the neighbors. So this way it makes the connectivity be with as compared to this point. So these neighbors are more closer to this data point than this. Therefore, this forms a continuity weight based clustering. That's why this kind of arbitrary safe or non-globular shape clusters are easily formed, right? This kind of clustering are also called graph-based clustering. Then there are some clusters which are called density-based clustering. So what is called a density? Basically, as we might have studied in our school days, density is basically the number of points in a unit volume, right? How many number of objects are there in a unit volume is called called the density of that plane or that space, right? So can you able to identify, apply such techniques to identify that the density, using the density, can you able to identify the clusters hidden in the data? So the here the best philosophy is cluster in a dense region of points which is separated by low density regions from other regions of high density. So if we look at this, this is a high density region and there can be some data points which lies here, which lies here. In the previous example, if you look at this, you see these are the smaller data points belongs to the low density regions, right? Number of data points in this region is less as compared to number of data points in this region, right? Which therefore we call dense region and sparse regions. So if you look at this, therefore you now see carefully, this is one cluster and this is one cluster because these denser regions are separated by low density regions or sparser regions. So if this philosophy is applied in the clustering, such clusterings are called density based clustering techniques. So again, any clustering techniques you look at or you want to develop, that depends upon some objective criteria. So we have two objective criteria. One objective criteria is how to suppose you are forming the clusters. So two objective criteria. One objective criteria is minimize the intercluster, maximize the intercluster similarity. That means all the data points within a cluster should be as similar as possible, and the intercluster similarity should be minimized, right? So between the clusters, the if you look at the distance between the data points between the clusters, their similarity should be minimized, right? These are two objective criteria. Based upon this objective criteria, we have objective functions, right? To how to maximize the intracluster similarity, and how to minimize the intercluster similarity, right? So these are the two basic objective criteria. And if you look at this clustering techniques, you will easily understand that suppose there are n data points given, and let's say simple somebody has told you that the data this set of data points simply contains two clusters, right? Then how many possible ways we can find two clusters? Any answer? Any answer from the students or from the audience? Suppose there are n data points, n data objects, forget about the dimension of the data, and you know that the data contains only two clusters. So how many different ways we can form the clusters? So if I have 4 data points, how many ways I can suppose data points are 1, 2, 3 and 4. So I have 4 data points. How many different ways I can form the clusters? So one cluster can contains 1 and other cluster can contains 2, 3, 4. Then another way you can say one cluster can contains 2, other clusters can contains 1, 3, 4. And then you say one cluster can contains 3, other can contains 1, 2 and 4. Sorry, 1, 3 and 4. Similarly, one can say one cluster can contains 1, 2, other clusters can contain 3, 4. So one can say no, one can contains 1, 3 and other clusters can contains 2, 4. So this ways, if you enumerate, you will find that number of enumeration will be exponential exponential, right? Therefore it's a hard problem to discover all possible clusters, and then among all possible clusters to identify which is the best clusters, right? So that is infeasible in practice. Therefore this is a challenging task because it's a NP hard problem. You cannot able to enumerate. It's not feasible to enumerate all possible clusters to identify the best set of clusters from them. Therefore, we have objective functions and we do some kind of approximation that if up to this level the objective criteria is satisfied, we are happy with that set of clusters and we say the best clusters are formed. But actually in the reality, the clusters formed may not be the best set of clusters, but it satisfies your objective criteria, so we are happy with it. So the objective criteria can be local objective criteria or it can be global objective criteria, depending upon which objective criteria is formed or employed to devise clustering techniques. We have different set of clustering algorithms. So K means is one example of a algorithm which employed global objective criteria, and then the hierarchical clustering uses local objective criteria. Then what is quality? Once clusters are formed, 1 minute, let me to take some water. So let us say we have formed the clusters. Then the next question will be, we have seen the similarity function. We have till yet not seen what are the ways to form the clusters. We have only seen different philosophies used to form the clusters. Now let us assume that a set of clusters are formed by some of the algorithms. Then the question will be how good the clusters are. Is there a way to quantify the goodness of clusters or badness of clusters? So yes, there are several numerical measures exist to quantify quantify the goodness of clusters. So it's a good clustering method will produce high quality clusters with a high intra-class similarity or cohesiveness within a clusters. So if you look at this, there are two clusters. So one criteria is the cohesiveness, the data points or objects within a cluster, how cohesive, how close those data objects are. And other is low inter-class similarity or called separation or called distinctive nature, distinctive between two cluster or called separation between two cluster. Separation should be as high as possible, right? So these are the quality of measurement. The quality of a clustering method depends on the similarity measure used by the method, its implementation of the algorithm, its ability to discover some or all of the hidden patterns. Then the quality of clustering, how to measure the quality. There is a usual separate quality function that measures the goodness of a cluster. In today's lecture, we are not going to cover it. In the lab session, we will see many such measures. It is hard to define similar enough or good enough. The answer is typically highly subjective or relative. Therefore, you find in the literature is full of such measures, but no one is a perfect measure, right? So therefore, still research is going on how to find such good measures to quantify the goodness of clusters. So some of the examples of this similarity, some of these quality measures are sum of squared errors, SSE, Rand index, adjusted Rand index, you might have heard about it. Similarity coefficient. In today's lab session, we'll see this quality measures. So there are many considerations before applying a clustering techniques. What is that? There can be partitioning criteria, which way you can partition. There can be separation of clusters. The data can belongs to exclusive to a single cluster, or data point can belongs to different clusters, right? For example, one document may belongs to more than one class, right? So one news article about a politician, let's say, can belongs to politics, it can belongs to sports, it can belongs to economic also, right? Finance also. So this kind of called clustering is called non-exclusiveness. The based on the similarity measure, it can be distance based, that's we have already seen. It can be connectivity based, it can be density based. Then clustering space, this is another problem in the clustering, right? When the dimension of the data is huge, the number of features is huge, so it can influence the clustering. It can also influence the classification. In the classification, you might have already seen about reducing the dimension, right? Their first thing is, if it's a high dimensional data, how to reduce the dimension and then work on the low dimensional data so that the classification accuracy can be improved. So the same problem do exist in the clustering we call curse of dimensionality. So if the data is high dimension, can we apply the clustering algorithm on the full data instead of reducing the dimension of the data? Or we can apply the first reduce the data, do a pre-processing of the data, and then apply the clustering algorithm over that. So that is called full space clustering. Then there are several requirements and challenges exist in the clustering, right? Discovery of clusters with arbitrary shape. Your data can contain, if it's a two-dimensional space, so you can see the cluster shape of the clusters. We have several examples next, so you can see this. So the shape can be anything, right? It can be concave, it can be convex, it can be spherical shape. So if this kind of data exists in your data, this kind of clusters exist in the data where shape of the clusters can be arbitrary, right, or irregular, how to identify them? It's a challenging task in the clustering. It's often easy to identify if the clusters are of spherical shapes in nature, but it is often difficult to identify clusters if they have arbitrary shapes. So ability to deal with noisy data, when we capture the data from different devices, right? So it can capture certain level of noise. So such noise level can influence, these are not the actual data, right? So in two-dimensional space, if you look at the noise, the data points actually supposed to be here, because of noise it can move little bit from its actual space to some other space, right? So that can influence the clustering, right? Then the data can also contain outliers, right? Outliers also can influence the clustering. So how to deal with such kind of data? Then insensitivity to input order, right? So the data, the way the data is captured, we can number the data, the object 1, object 2, object 3, object 4, and so on, right? So when you cluster the data, so the clustering algorithm should not depends upon which order these data items, data objects are being supplied, right? So that is called insensitivity to input ordering of the data. Then another factor which we should be worried about is scalability. The clustering all the data instead of only on sampling of the data, right? So it can be often observed that the when the amount of data is huge, number of objects is huge, or dimension is huge, finding the clusters hidden in the data can be a challenging task, right? You need very sophisticated computers to process the data, because it's a challenging problem, right? The most of the algorithms, the complexity is quadratic. Processing such huge data in desktops is often difficult, so we go for high-end computing facilities to do it. Even when you have millions of data points, processing those data in a high-end computer is also a challenging task. So how to deal with such data? Can you do the sampling, or we should not go for sampling, right? So that is called a scalability issue. So there are many approaches: partitioning approach, hierarchical approach, density based approach, then grid based approach. So today we'll see partitioning approach. If time permits, I'll go for hierarchical approach. Otherwise, we'll mainly discuss about the partitioning approach in the clustering. So the clustering algorithm, very popular algorithm, developed in 1950s by several multiple researchers independently. The official document probably was published in 1963 perhaps, by Steinhaus as the author. So the algorithm is popularly called K-means. Several versions do exist nowadays, but it's widely used algorithms because it takes less time. Though there are many sophisticated algorithms have been developed over the years, but still this algorithm is very popular. So we'll see this K-means algorithm in today's lecture. So it's a very simple algorithm, very easy to understand, very easy to code, and very effective, highly effective on most of the data. So it employs partitional clustering approach. Number of clusters k in the data is k must be specified. So in priori, we assume that k is given to us. Number of clusters are known to us as a user. So we supply that as a parameter. Each cluster is associated with a centroid, or the mean point of the data. Each point is assigned to the cluster with the closest centroid. Therefore, this is called centroid based clustering. We are considering only for numerical data. Therefore, we call centroid or the mean point of the data. So this algorithm is a very simple one. Sorry. So the pseudocode is given here. So first is k is known to us. So you select k points randomly as the initial centroid of all the data. So given n data points, you select k data points out of n points randomly, right? Then what you do is, in the next step, form k clusters by assigning all points to the closest centroid. Then once all n data points are assigned to k cluster centers, then recompute the centroid of each cluster. Then repeat these two steps, right, till the centroids are not changed. So stop when there is no change in the centroids. So this is, the algorithms looks very easy to understand and very easy to code. So let us see this through example now. This is two-dimensional data points, and here if you look at the data points are plotted in two-dimensional plane. X-axis, the data points vary from -2 to 2, and y-axis it is from probably again -2 to 3. So suppose this set of data points are given. This is for just for your sake of pictorial visualization. So we compute three such data points as cluster centers. You choose three data points randomly. For example, this data point, this data point, 1 minute please. So this data point, and this one, these three are chosen as cluster centers. Now take any point in the data. Let's say this data point is considered now, right? And find the distance of this data point from from three cluster center, this, and this. Let's say the distance here is Euclid distance in the two-dimensional place. So when you compute the Euclid distance from any data point, so what is the nearest cluster center, right? So suppose in the Euclid distance, this value is 10, this value is 8, and this value is 5. So this is the nearest cluster center. So this data point is assigned to a cluster where this, let's say this is X, this is Y, and this is Z. So this Y is the cluster center. Similarly, when you take this as a data point and compute the distance between these three cluster centers. 1 minute please. Cluster center distance from this, distance this, and distance this. So this distance. So you find this is again the nearest, right? So this data point will belongs to a cluster where Y is the cluster center. Similarly, if you take this cluster center, then what happened? Again, we will compute the distance of this data point from the different cluster centers. These three cluster centers, one distance is this, second distance is this, and third distance is this. So this one is the nearest one, Z. So this data point will belongs to the cluster center where Z is the cluster center. So this way all the data points are assigned to their nearest cluster centers. Therefore, since there are three cluster centers, three different clusters are formed. Now what is the next step? So in the iterative step, what to do is we repeat the process continuously. So now what is the next cluster centers? So this green data points belongs to a single cluster. So take the arithmetic mean of all these data points. So then this red data points belongs to a single cluster. Find the arithmetic mean of all these data points. Then this blue data points, find the arithmetic mean and find their centroid. So what is the centroid now? If you look at carefully, the new centroids are formed now, right? So they may not be actual points. They are just the arithmetic mean. The arithmetic mean may not be the actual data points, right? So it can be imaginary points. So these three cluster centers now are computed, and these 3 are not the actual data points. They are marked as plus symbol. So now again reassign or redistribute all the data points, take any data points, right? And then find the distance between 3 cluster centers and assign the data points to the cluster having the nearest cluster center. Okay? So in that way, we reassign the data points to different clusters. Now you look at carefully, observe carefully, these were the 3 clusters. Now these data points are redistributed to 3 clusters. So some data points have been redistributed to different clusters, and some data points remain in the same cluster, right? So for example, these data points were in the first cluster and that remains in the same cluster. These data points already were in the green colored cluster, that remains as it is. This data points were in the blue cluster, that remains as it is. But this data points were previously in this green cluster, but now they are assigned to the red cluster, right? So now again repeat the same step till there is a change in the cluster center. So when you do this, again look at this step, then recompute the cluster centers using all the data points within a cluster. So suppose green, blue and red clusters are formed. Now take those points separately, find the arithmetic mean, call that as a center of the cluster. Now you find the cluster centers, they are moving and data points are also moving, right? Are getting redistributed. Now again repeat the same process. So when you repeat the same process, you find there are again different clusters, the centers are moving, the points are being redistributed to their clusters. Now again recompute the cluster center. Again you see some points are only few points are moving from here to here. This was the previous step, this is the next step, right? So I think only one point is moved. This point is moved to this, it was here and it is now moving to the red cluster, right? And all of the other pointers remain intact. And then again we recompute the cluster center. You see that now no point is moving from one cluster to other, right? And then again when you recompute the cluster center, you will find that clusters and either the cluster, when cluster centers are not moving, then obviously the data points also will not move from one cluster to other, right? So that is what is our stopping criteria. We should stop there, right? When the cluster centers are fixed, right, in conjugative 2 iterations. So this is how the K-means algorithm works, right? So here this initial centroids are often chosen randomly. Clusters produced, therefore the cluster produced vary from one run to another because of randomly chosen cluster centers. The centroid is typically the arithmetic mean of the points in the cluster if the data is numerical. Closeness is measured by Euclidean distance. It can be cosine similarity, it can be correlation or any other measure that you can apply. K-means will converge for common similarity measures mentioned above. What is convergence here? So the convergence here is how this how do we guarantee that at some iteration, after some iterations, the centroids are not going to be changed? How to guarantee? It may happen that the iteration can go on and on for infinite number of times. It may go into an infinite loop where in every iteration the centroid may get changed, right? So the algorithm will never stop. However, it guarantees that this is going to stop, or this is what is the convergence criteria. The convergence criteria does not give you any guarantee about the types of clusters formed or the quality of clusters discovered. it gives you only the guarantee that if you apply k-means, the cluster centers are going to converge to some point. It will never change after that, right? So that is what is your stopping criteria, or called convergence criteria, right? So most of the convergence happen in the first few iterations only. You may not have to apply 100 iterations of k-means in the real applications. Hardly you will see that in 5-6 iterations the k-mean convergence. In most cases maximum 10. So complexity, what is the time complexity of algorithm? Why this algorithm is so popular? Though there are several issues do exist, because it's almost linear complexity, right? So the complexity of the algorithm is n, KID, where n is number of objects in the data, I is number of iterations, k is number of clusters, and d is number of attributes. You see carefully, this complexity of the algorithm depends also on the number of iterations. Mostly when you analyze the algorithm, we see that it doesn't depends upon the output of the output or the convergence criteria, but here the complexity depends upon the convergence, how fast the convergence is. If I is very large, then the complexity is all the time taken by the algorithm is going to increase, right? So why this time complexity is nkid? If you just look at this carefully, you see that in the first step, what you do, you choose k cluster centers randomly, and we compute the distance of every data points with the cluster centers. There are n data points in the data. You have to find the distance between n data points with k cluster centers, right? So exactly for each data points, k distances has to be computed. Let's say Euclidean distance. So for each data point, you have to compute k distances. So for each distance takes d amount of time. D is the dimension of the data, right? So for each data point, k distances has to be computed. Each distance takes d amount of time, d number of operations. So for each point, data point, kd amount of operations are required, right? So that has to be repeated for n data points. Okay, so this is the amount of operations required for all n data points in a single iteration. So how many iterations we have to apply? We have to apply I iterations when the algorithm converges, or your program converges. Therefore, the complexity of the algorithm is nkdi. N is the number of data points, k is the number of clusters, the dimension of the data, and I is the number of iterations of the algorithm. So as I have told you, always there is optimization criteria, local optimization or global optimization, right? So k means applies global optimization. So which factor is optimized in each iteration? Though we say that it is the cluster centers are moving, and that is the way we identify the moving criteria or the stopping criteria, but there is a same as the saying that in between two iterations the cluster, the centroid is not moving, is same as minimizing the sum of squared errors, are famously called SSE. You might have seen this also, this way of computation of error in case of supervised learning. This is used in the k-means. To get this SSE, we square this error and sum them, right? So what exactly we are doing here? So you see this first sum, this is I varies from 1 to k. For each cluster, we have k clusters. For each cluster, we are computing the sum. So what sum you are computing? So for each data, for each cluster CI, for each data point in the cluster CI, what we are doing is we are computing the distance between mi is the cluster center, x is the data in the cluster. Suppose we have two clusters like this. So this is cluster center CI, and this is, let's say, cluster center Cj. So you take any data point here, find this distance, square distance, right? Not exactly the Euclidean distance, the square distance. Take the sum of all these square distances. Here again, take the sum of all these square distances of any data point in a cluster with its cluster center. So you are actually taking the sum of all this. So this is x belongs to ci. Let's say this is c1, this is c2. So for I varies from 1 to 2, x belongs to c1. This distances are computed. Take the sum of all this. So this is called SSE value, or sum of squared error. So the algorithm stops when there is no change in the SSE value, right? This is considered for all the clusters, therefore it is a global optimization criteria. So the k means actually optimizes this. Okay. So two different k-means clustering. So this is given the set of data points remain same. This is one set of data points. But if you look at this carefully, you can apply k-means by randomly choosing cluster center. One k-means can produce, so k-means, the k-means, one run of k-means can produce, one run of k-means can produce this cluster, and other run of k-means, same algorithm on same similarity function, can also produce this kind of clusters. So we look at this. This is almost good clusters are formed except these two data points. All other data points are properly grouped, right? But if you look at this, this is very bad clustering. Bad clusters are formed. This large cluster is splitted into two different clusters. One is this blue and one is green. So k-means can also produce this kind of clusters. So what is the solution? The solution is, since the cluster centers are chosen randomly, so one run of k-means cannot be trusted, right? You cannot say good clusters are formed, you are happy about one run of the k-means. So what exactly we can do? You can apply k-means maybe 10 times, right? Not number of iterations. Number of iterations is a converging criteria. But run k-means n number of times, let's say 10 times, and then see out of 10 times what is the best set of clusters formed, and consider that is the best set of clusters produced by k-means, right? So the k-means can produce in one run, k-means can produce suboptimal clusters. In another run, k-means can produce good set of clusters. So what are the problems of k-means? Is it very popular, but then can it be applicable for all kind of data? So the answer is no. Though this is very popular because it's easy to understand, easy to code, publicly available codes, very old algorithms, people have been habituated with it, right? Very simple to understand. But k-means a serious problem. So when clusters are of different sizes, then different densities, then it contains non-globular or non-spherical shapes. So k-means also a serious problem. So when the data contains outliers or noises. Let us see one by one. Let us see, this is an example of clustering where the data contains clusters of different sizes. So if you look at this three clusters here in this two-dimensional data, you find that this is one cluster in red, green and blue. So this is a bigger cluster and the other two clusters are relatively smaller. So when you apply k-means here, you see that whichever way you apply k-means, maybe you can choose a cluster center here, here and here, but still you see that because of near centroid based clustering, this larger cluster will be split into smaller clusters. Therefore you see this kind of clusters are formed, right? So this is a serious issue which came in. So when the clusters are of different sizes, one cluster is very big, other one are smaller. Other issue is clustering is different density. As I have told you, your data can have different set of clusters. One can be highly dense region, other regions can be sparser regions. So here the red region is a sparse region, whereas this blue and green regions are what is called uh, uh, dense regions, right? The number of data points within a unit area is huge, or number of data points is more as compared to this region, right? Therefore, when you compute this, right, again there will be problem wherever you take the cluster centers, but again this kind of bad clusters will be formed. You see this sparse region will be splitted into several clusters, right, and dense regions can be merged in between them. They are more closer to each other than the points in sparser regions. So because of that, since it's centroid based, you see the centroid will be moved to here, and all the data points sparser regions is relatively bigger and they can be split. And then when the clusters are of non-globular shapes or non-spherical shapes or arbitrary clusters, that is always a challenge in the clustering. So if you look at this carefully, these are non-globular shapes. One is blue clusters and one set of data points are in a represented in a red cluster. So these clusters are not spherical shape clusters. So whichever points you choose as cluster centers, so the best clusters the k-means can produce is this, which we can see in the right. So the cluster center, wherever you choose, this way the spherical shape clusters are going to be formed, right? So this is not a useful algorithm when the data contains non-globular or spherical shapes, right? So the obvious question one of you can ask is how do we really know if your data contains globular clusters before applying k-means? If your data contains globular clusters, yes, obviously k-means is the best algorithm to apply. Then the question will be, how do we know your data contains globular clusters or not? We assume very little domain knowledge is allowed. So it's still an open problem to know, given the data, can you able to say that the data contains globular clusters or not, or what kind of data it is, how many clusters are hidden in the data, how many what shape of clusters are, or how many different density regions are, right? So all these are open problem. Nobody knows the answer in machine learning, right? These are challenging data science problems. So maybe some of you can take up all these challenging problems and can come up with some solutions. So is there a way to overcome these k-means limitations? There are several variant of k-means algorithms proposed. This is the basic algorithm that we have discussed. Several variant of k-means algorithm exist in the literature, right? So how do we overcome this problem? So when it is of different sizes, right, one solution is to use mini clusters, find part of the clusters but need to put together. For example, instead of finding 3 clusters here, if you find several clusters, supply several cluster centers, you see how these clusters are formed. Smaller clusters are formed, but if you observe these points or clusters that are formed here very carefully, you will observe that all these smaller clusters contains data points belonging to a particular data, right? Particular cluster. For example, this larger cluster now is split into several clusters here, right? So however, if you pick any cluster, smaller cluster here, you will find that all the data points belonging to these smaller clusters, they all belongs to only a large cluster, right? So that is one advantage. Now the next question will be, once these smaller clusters are formed, then how to identify the actual clusters? So next question will be, can we able to merge these smaller clusters to form the actual clusters? So can these smaller clusters be merged among themselves so that we can have three cluster. One is this, one is this, and one is this, right? So can we able to do this? So that is another challenge, how to identify, how to merge these smaller clusters. So in this case, the next algorithm, which is the hierarchical algorithm, which is very famous, that can be very helpful here. So to combine two algorithm, one is k-means, that can be applied as a pre-processing step, right? You apply k-means to identify smaller clusters. Then once smaller clusters are identified, then you can have your own merging techniques to merge these smaller clusters to identify the actual clusters. So you can apply the hierarchical algorithms to identify the hidden hierarchy in the form of smaller clusters, right? So that is one of the way to overcome the challenges in limitations of k-means. So here is another examples in the density variation. You see now the sparse region can be split into smaller clusters. They form smaller clusters which taken the data from a single cluster only. So that is a good thing. Clusters are actually formed. So now our aim will be to merge the clusters. So you can go for hierarchical clustering. So here also, if you look at apply k-means, see nice clusters are formed. So instead of 2, 8 clusters are formed. So those clusters are very spherical in shape. They all have taken data points belonging to a single cluster only. So next challenge will be how to merge these two clusters. So you can apply the connectivity based rule to merge all these clusters into a single cluster, and the data points, the clusters here, to find the actual clusters. So this way you can overcome by combining the hierarchy k-means with the hierarchical clustering. So many students or many researchers have been working on how to merge these smaller clusters to identify the larger clusters. So here our students have been working on developing these merging techniques to identify the smaller clusters. We have been able to develop heterogeneous clusters through merging. Then again, you say the challenges in clustering is how to identify this initial centroid, importance of choosing the centroid. One example, so we have already seen. So if you choose these 3 cluster centers here, it can able to identify the actual clusters, right? But however, if you choose cluster centers like this, then you see that once this cluster center is chosen, obviously all these data points, this cluster center will move towards this, and obviously to take all the data points belonging to 2 clusters into a single cluster, and this cluster center will move towards center of this, and this will form bad clusters, very bad clusters, right, like this. So now the question is, k-means probably will work better provided you choose cluster centers randomly, each one cluster center from each of the clusters. So what is the probability of choosing a cluster center from each cluster? So since we know there are 3 clusters in the data, what is the probability of choosing one cluster center here, one cluster center here, and one cluster center here somewhere in the data, right? So we'll see that this probability is really negligible. So if you can able to identify this cluster center from each cluster, then most likely you are going to get good clusters, but that probability surprisingly is very less. So what is the probability? Let us say that there are k real clusters, then the chance of selecting one centroid from each cluster is negligible. So what is the chance? Let us say there are n data points in each cluster. So how many number of clusters you have? So each data points, let me draw. So each cluster have n data points, let us say evenly distributed, and there are k clusters, so there are total nk number of data points, right? So therefore total number of data points is n and k. So number of ways to select k centroids, so there are nk data points. So out of that you have to choose k points randomly. So repetition is allowed here Therefore, any point can be chosen repeatedly k number of times. So in the worst case, number of ways to select k centroids out of nk data points is kn whole to the power k. Clear? Then from that R image, what is the probability of choosing a cluster center from each of the k clusters, right? So each cluster has n data points. So choosing one data points from each of these n data points is n to the power k, and when k cluster centers are chosen one from each of the cluster, then they can be arranged among themselves in k factorial OH. So this is basically k factorial n to the power k divided by k n to the power k. So n to the power k and n to the power k cancelled out here. So factor is k factorial divided by k to the power k. So the probability of selecting one centroid from each cluster is very small because it depends on the number of clusters. So if the number of clusters k is 10, then this value becomes 0.00036, is highly negligible. It's highly unlikely that you are going to select one centroid from each cluster, right? So since this is negligible, sometimes the initial centroid will readjust themselves in right way and sometimes they do not. We have seen this. So this kind of example we have already seen. Let us keep this one, right? So now the question will be, is there a way to overcome this, selecting these cluster centers? There are many variants of this is available. So how to overcome? One is multiple runs. This helps. The probability is not on our side, right? You can apply k-means as I have told you 10 number of times, then see which clusters are the best clusters formed out of 10. Use that set of clusters. But then probability is very negligible. The any number of times you use the initial centroid may not be properly chosen. That can influence the clustering technique. Select more than k initial centroids and then select among these initial centroids, right? So you select k more than k initial centroids and those centroids should be widely separated. What exactly, why this kind of situations we are facing? So we are facing these situations because if the centroids are very close to each other, that will not represent the true distribution of the data, right? So if data is like this and you choose cluster centers like this, or you choose two cluster centers somewhere here, right, it actually does not represents the does not capture the true distribution of data. Therefore this is the problem. But however, if you choose this cluster centers, two cluster centers, one is here and one is here, they are well separated, then it actually captures somehow the true distribution of the data, and some data will be closer to this will go to this cluster center, and the data which are closer to this cluster center will go into it, right? So most likely few points will be here and there, but clusters are going to be formed. So the problem is how to select those initial cluster centroids. They should be well separated. You can also post process generate a large number of clusters and then perform a hierarchical clustering. We have seen the example. Then another very popular clustering variety of the variant of k-means is called bisecting k-means. This is not as susceptible to initialization issue. So we'll see the bisecting k-means. Then there are other clustering techniques called k-means plus plus, right? Our students also have proposed k-means algorithm which are very good, produces very good results, called dk-means, right? So today we'll discuss the simplest one called bisecting k-means. So this is variant of k-means that can produce a partitional or hierarchical clusters. So this is again uses k-means. So initialize first the list of clusters to contain the cluster containing all points. So initially we have a single cluster C. So select a cluster from the list. So you have a single cluster. Then for I varies from 1 to number of iterations of k-means. Number of iterations are not known. bisect the select cluster using basic k-means. So what you do is, in the k we always provided 2, we produce 2 number of clusters, so therefore this is called bisecting k-means. So given the first iteration, you bisect the data into 2 clusters, 2 clusters are formed, then which cluster contains large number of data points, again we bisect that into 2, then out of 3 you identify which cluster contains more number of data points, then their difference is more, you then bisect that into another 2 and so on. So do this until k number of clusters are formed, right? So this is called bisecting k-means. Let us see through one simple example for which k-means will fail miserably. So this is a data which contains 10 number of clusters, right? So this is actually the data, right? So all these are 10 clusters formed here. So k-means forms miserably on this data. So if you apply suppose apply k-means, taking 2 cluster center randomly somewhere, so obviously only 2 clusters you are forming, you are not forming 10 clusters initially. So most likely somewhere the cluster centers are chosen and now 2 clusters are formed here, right? So if you look at the SSE value, compute the SSE of this and compute the SSE of this. So the error rate is here more because this is the cluster center and the distribution of data is widely distributed. So distances is more. So sum of square distances is going to be more. So SSE value is going to be more. So since SSE of this is more, so choose this for the next iteration of k-means, then apply again k-means here in the this light blue clustering. So you will see that when you apply this k-means again, so by bisecting k-means, that means only 2 cluster centers you are supplying. So one of such clusters can be produced is this, one is this and one is this. So now we have 3 clusters. Again compute this SSE of this, SSE of this and SSE of this cluster, right? Then find which SSE is maximum. Let's for example this SSE is maximum. So this is a candidate cluster for applying by-means again. So apply next iteration of by-means. Sorry, here SSE is more in this example. So apply by-means again. So this is split into 2. Then again recompute the SSE of this and SSE of this green cluster. So obviously the SSE of this is going to be more. Then again apply k-means here with 2 cluster centers. So produce 2 cluster centers, one is this and one is this. Recompute the SSE value and then continue producing till 10 clusters are formed. So this is different iterations of producing clusters by by-means algorithm. So here we have 3 clusters. Next iteration we form 4 clusters. Next iteration we split this and produce 5 clusters. Next iteration we split again this into 2 and produce 6 clusters. The next iteration probably will split this and produce 7 clusters, right? Our next iteration again will split another one and will split this and produce 2 more clusters and so on, right? Now we have 10 clusters. Then apply the k-means on this 10 clusters. So a little bit of movement, this data is going to this. So now if you look at this, the actual clusters are formed, right? So this is one of the variant of k-means called bisecting k-means, right? So you can also pre-process the data. Probably pre-processing and post-processing are majorly done in supervised learning. In the pre-processing you can normalize the data so that the scaling factor can be taken care of. So if you are applying Euclidean distance measure or Euclidean like distance measure, it can highly influence the clustering, because suppose one feature, let's say price of a car, it can be let's say 50 lakhs, right? and color, and let's say uh, the what is called cost. Uh, Suppose some data, some there are two features or three features, F1, F2, F3, and F1 value can be 50,000, and this value can be 60,000, and this F3 feature value can be 2 and 3. So when you apply, and this feature value can be 4 and 5. So when you apply the Euclid distance, you see this distance is going to influence everything. These two features have no role, almost negligible role in the distance computation. Therefore, sometimes normalization of the data is required. You might have seen this. This is majorly done in case of supervised learning. Then you can also identify and eliminate the outliers which are out of the clusters. In the post-processing step, you can eliminate small clusters that may represent actual outliers, split loose clusters with relatively high SSE so that the minimize the error rate, merge clusters that has closure enough and that have very relatively low error rate, so those clusters are potential candidate for merging, right? So you can apply this pre-processing and post-processing steps in the clustering to further improve the clustering quality, right? So I have taken this material from lecture notes, basically chapter 7 of the book Introduction to Data Mining by Bipin Kumar and co. This is publicly available at this website. Then some materials are taken from Concept and Techniques, third edition, Data Mining Concept and Techniques, third edition book of this. And some of the materials are taken from publicly available sources of IIT KGP to prepare these slides. So I thank all the original authors from where I have taken the slides. So now let us have some discussion. You can ask if you have any doubt. Some of your doubt I can able to probably answer. Some of the questions I may not be able to answer. I'm still learning clustering. I'm a student like you. So it is open. You can ask any question if you have.
There are some questions, Sraban.
Yes.
Sir, can clusters need to be classified? Sir, any recent research area on clustering?
So actually I don't know what is the meaning. Classification and clustering are two different problems. Classification is supervised learning where you have a model based on your past experience, right? On such data you develop a model, and when a new data, suppose customers in a bank, right? All the customers in a bank. So bank has a model, existing model. So when a new customer arrives, suppose you are applying for a loan in a bank. So how the bank can decide whether the customer should be given or approved the loan or not, right? How the bank can decide. So that is a classification problem. Clustering is when the data classes are not known to you. The whole bunch of data is given to you and there are hidden characteristic of the data. You have to just group the similar objects, right? So I was giving example of document clustering where the set of documents are given. Let's say today's newspaper. If you browse through the newspaper, some articles are sports related, some are political, some are finance related. So can you group all such articles depending upon some keywords, right? Which articles are sports, they should be grouped together. Those who are political related, related to politics, they should be grouped together. So this problem is called clustering. So these two are basic fundamental problems in machine learning. So I do not get your question. How classification in done in clustering? What was the second question, ma'am?
Second, is there a condition to choose minimum number of clusters?
No, actually. Many cases we assume that number of clusters are given to you. This is your domain knowledge. And many cases even we do not know how many clusters are there in the data. So when the number of clusters are not given, it's really a challenge to identify the number of clusters. So what exactly you do in k-means, since we have discussed k-means. So in the k-means, our aim is to minimize the SSE. And from the example, if you remember, so more the number of clusters, obviously the SSE value is going to reduce, right? So if you start with 2 clusters and then you start with 4 clusters, so obviously the SSE value of 4 clusters is lesser than the SSE value in the 2 clusters, because the square distances is going to be reduced. The data points are going to be more closer to the cluster center. So the SSE value is going to be reduced. So where exactly we are going to stop then, right? So when the number of clusters are not known, then one criteria is you keep on keep on reducing the number of clusters, right? And see what is the difference between the SSE value. So when there is not much difference between two runs of the k-means in their SSE value, so we say this is probably going to be the k or number of clusters. So there you can stop, right? So that is one of the criteria.
So another question is there.
Sorry.
Yeah, please, ma'am.
No, one question from Dr. Ajik Ayagiri is that they want some textbooks to be, if you can share the names of the textbooks. So you can, that is what he wanted.
Yeah, the slide will be there. So here there are 2 textbooks. These are very good textbooks. You can go through it. Introduction to Data Mining, second edition by Bipin Kumar. So this is freely available in this web page. You can note down. Another is Data Mining Concept and Techniques. Right, this is the most popular book in data mining, and clustering is 2 or 3 chapters. You can go through it if you have interest. Yes. Any other question?
So how to use clustering in deep learning?
Clustering in deep learning. Already there are many deep learning models developed for unsupervised learning. Clustering in deep learning is a technique, right? Like the classical machine learning techniques that we are studying. This is classical means clustering techniques we are learning, k-means or DB scan, right? Similarly, the models what is called neural networks have been developed for clustering, doing the same thing. So you might have seen many deep learning models for classification. So you also have models developed for clustering. So problem remains same. Techniques to solve them are different, right? Deep learning is one of such technique, and these techniques that we are discussing here are other way of solving the same problem.
So how to predict behavior of different group in clustering?
How to predict different groups means what? You want to say that which set of clusters are good clusters? This probably is the question, right? So there are many measures exist. One such criteria is SSE. So you compute the clusters, set of clusters. Let's say you have data of n objects, and you have you apply 4 number of algorithms, and all 4 number of algorithms produces 4 different set of clusters. Then your aim is which set of clusters or which algorithm produces the best clusters. This is what probably is your question. So then the answer is, one such thing is you find out the quality of clusters. there are many ways to quantify the quality of clusters. One such example is SSE value. So let's say you compute the SSE of different clusters produced by different algorithms. So whichever algorithm produces the clusters having minimum SSE, you say those are the best clusters. So in today's lab session, we will see different measures, quality measures called RAND index, adjusted RAND index, SSE, right? All this we will discuss in today's lab sessions. So that is already planned. So one question is, which distance measure is best? You cannot say anything. Depends upon the data. Depends upon your depends upon the domain knowledge. But only thing you have to be very careful is you do not apply this randomly. Look at the data is numerical or data is categorical. Then only you decide which distance measure is suitable. If it is categorical, go for categorical distance measures. People often make a mistake. They do not distinguish between the characteristic of data. They treat all the data as numerical, because we human beings are more acquainted with numerical data from our school days. So you consider everything is numerical and apply numerical distance measures, which is a major mistake.
So lot many questions itself, and lot many thanks there are telling the story of this session. And I have also attended this, so I mean, I'm so glad to see Dr. Sraban here delivering this talk. And I would like to tell you all that Dr. Sraban has joined just after completing his PhD. He has joined IIITDM Jabalpur, and I have seen him growing.
Ma'am,
So
already there was a big introduction by
yeah, actually I
ma'am.
have missed that because I was also having a talk in another conference, so I missed the starting. But yes, I'm feeling I mean good, and I wish to share this with participants, so that is why I'm saying that. So it's a really my pleasure to see him now grown up in this area. And uh, thank you so much, Shravan, for this excellent talk. And I mean, I'm happy that the participants are enjoyed it a lot. And of course, I have also enjoyed it. I have joined a bit late because there the schedule become late. But yes, thank you, Shravan.
Thank you, Sravan. Thank you, Preeti. Thanks all the participants. We'll be meeting at 6. Please join before 6.